Good morning, everybody. I wanted to thank everyone for participating in the algorithms thread Treaps contest that I made. It was a nice contest and a whole bunch of people participated. We had over 100 solves on problem A, which was great to see. And on top of that, on top of just a lot of people participating, it's great to see that a lot of people are learning a new thing. So although the turnout was lower than the tree basics video, I'm pretty sure almost everyone saw that coming. It's great because a lot of the people who submitted for problem A had to go over some pretty big hurdle of learning a brand new concept and then trying to adapt it to something harder in order to solve the problem. So that's really a great thing to see. Today I want to talk about the solutions to each of the problems. So we had 5 different problems, and then Speeches and Sneatches was supposed to have 2 different subparts that were a little bit easier. There were technical difficulties with that, and when I was trying to modify it, one of the problems got deleted somehow. I'm not really sure how, and we didn't want to add it back in because that would mess up the order of the other problems, so people might get credit for solving a problem they didn't actually solve. But anyway, there were those 5 problems with the one extra easier version of Sneatches. And I'm going to talk about the solutions to all of them today. If you're interested in the solution to just a particular problem, you can skip to that point in the video. I'll have timestamps for what is when in the description. And if you just want to see the solution code, I'll also put that on the GitHub. So the same GitHub that had the Treap code that I talked about in the algorithms thread video, you should be able to see all of the solutions to each of these problems, and they're just my judge solutions. So those are the intended solutions to everything. All right, very cool. So let's talk about the problems. The first problem was Shandom Ruffle. So the nice part about this problem, I thought, was the same reason that quicksort is usually fast. It's usually n log n. That same reason is the same thing that makes Treaps usually be very short. So Treaps usually have a height that's only log, because when you pick randomly, or when you pick your split point randomly of quicksort basically, chances are you'll pick it in the middle. Well, you can construct some case that's very adversarial, or you could get really, really, really unlucky when you're making your Treap. And in both cases, you might either have a bunch of different pivots that all have very big arrays and split it very poorly, or when you make your Treap, you might pick the leftmost element every time or the rightmost element every time. So this kind of operates on that principle, and that's why I thought it was an appropriate idea for the problem. What is this problem? What's going on here real quick? So let's talk about that. So the way we Shandom Ruffle this array here, let's make a new whiteboard, is we've got a bunch of elements, and the idea is if we shuffle the array before we call arrays.sort, then they won't be able to predict how it's shuffled. So that's what we want to do. In order to do that, we're going to pick 2 pointers like this, maybe this left point and this right end point, and we're going to swap these 2 elements with each other, and then swap these 2 elements, and swap these 2 elements, and then we're going to keep going until one of 2 things happens. Either we run out of things in this group, or in this case, we run out of things in this group. So the second thing happened here, which means we would only swap 3 things. So if we look at this group here, and then this group here, we'll swap the first element with the first element of the other group, the second elements, and the third elements. Now the key observation for this problem is there's an easier way to think about that, and that is instead of making a bunch of individual swaps, we can look at this as a big range swap. So we can say what we need to do here is cut the array here, cut it here, and then if there's anything after, we need to cut it here. And now we have some parts. So we've got part 1, part 2, part 3, part 4, and we have a part 5 as well. In this case, part 5 is empty. And once we've done all these splits, we need to glue them back together. So when we're done, we want the order to be 1, 4, 3, 2, 5. So that's the idea behind the problem. And if we have a Treap that lets us cut and merge these 2 pieces together, this is exactly what we want to do with it. So it's a great kind of more introductory use case for when you can have a Treap and what it's useful for. Then at the end, we want to print the shuffled array. So that's an easy enough thing to do, I guess. So yeah, the input just starts as some permutation, and we're given a bunch of L and R endpoints, and we want to do some swap like that. Let's talk about what the code looks like. So this is the Shandom Ruffle solution. I'll make the text a little bit bigger so people can read it. And I won't go over the exact like Treap code here because this is pretty simple. This is almost exactly just what's on the GitHub, but I will talk about this part because I think it's good to know how it works. We read in n, and then we merge a bunch of things to the right. So we have initially just an empty Treap, it's just nothing. Then we make something with element 1, element 2, 3, 4. We keep merging the next elements to the right, which means the array that we're representing starts out as just the permutation 1 to n. Just 1 followed by 2 and 3 all the way up to n. Then we have a bunch of queries. For each of these queries, we'll read the left endpoint and the right endpoint. And then we look at the size, which is we want to figure out which side ends first. So is it like the left part that runs out of room or the right part? Once we know what that is, we know we go from the left to left plus size minus 1, and then same thing for the right. Now here I just split it up a bunch of times. The math here I guess is a little bit confusing, but I'll walk through it. The idea is first we've got like a bunch of things. We've got like stuff like this. We'll have some position here, so this is like position A, then we also have the position B. So first I make the two halves. So the first half, halves at 0, will be this part of the array, halves at 1 will be this part of the array. So then this halves at 1, this is this part. This first part here. I want to split it at position A. So now I'll split this into two groups. So I'll have this first part followed by the second part. So this is what this part is for this array. Then I want to split this group as well. So once I have this, like I have to get the size of this group. So it's possible, for instance, if the array looked like this, that we actually want to split this first half into two different parts. So I do this split here, and that'll get me this part of the array which needs to be swapped with this part. Then for the second half, we also need to split that in case the first half was the limiting factor. So an example would be like this. In that case, we want to split this here. So we also split this into two parts. And then finally, we merge everything back together very carefully in the correct order. So it's a lot of like, be careful with your merging, be careful when you draw stuff out. And then this is like a working way of doing it. I'm sure there are other ways of doing it as well. Finally, at the end, we just print what it looks like. So yeah, that's the idea behind Shandom Ruffle. Basically, the important part is if you go back to the picture, you need to cut it up into your 5 different pieces and then swap pieces 2 and 4. So you need to be able to do that with the Treap using splits and merges. Awesome. Okay, that's problem A. And that idea will come back for quite a lot of other problems as well. Let's talk about problem B, Pear Treap, because that was the next most solved problem. So the idea here was we're going to do some operations, and we want to figure out if different substrings are a palindrome. The first operation is range delete. So we want to delete some range of characters. We should be able to do that without too much difficulty. The second thing is we want to insert some character, which we can also do without too much difficulty. And the next thing is this some substring, or is some substring a palindrome? Which is kind of the tricky part. Because we could do this, we don't have to worry too much about that. It should be pretty easy to handle. Inserting, I guess, is a bit tricky, but if we have a Treap, we can split and then put something inside and then merge. This substring part is very tricky. Checking if a substring is a palindrome that's quite the challenge, because like we can't just check the whole thing because the substring might be really long. So we might make this query run in linear time if the substring is big. And that's not something we want. So what we can do to handle this is actually use hashing. If you're not familiar with hashing, that's a pretty big prerequisite for this problem. So this problem, I guess, probably isn't a super good one to work on at the moment. But if you are familiar with hashing, you'll know one thing you can do is append 2 hashes. So in this case, if you have some prefix, let's say you've got something, you've got some string like this, you have the hash of this, you also have the hash of this. What you can do in order 1 is get the hash of this entire range. So that's what we want to do. If we have some Treap and it's got some left treap here, some right treap here. These might be empty, they might not be. We can get the hash of this entire range by saying, okay, what's the hash of this treap? We can store that with like as a subtree aggregate. Then we can append the hash of this value right here. And then finally we can append the hash of this treap right here. So by doing these hash appends, we can get exactly what we're looking for. That can give us the hash of some substring. So we can get some substring hash very quickly by splitting here. We can do this split, get this hash. That's what we're looking for. If we want to see if this thing is a palindrome, we can store another copy of the treap, but that other copy will be backwards. So we'll have the hash of the forward version, and then if we had this mirrored, we would have some other substring that we're interested in. Maybe it would be this substring here. And if the hashes of these two substrings are the same, that means it's a palindrome, because that means this substring is the same forward and backward. Briefly, what that looks like is I've got two treaps. This one is forward, this one is reversed. And I build them in kind of an interesting way. The forward one, I always add the character to the right end. For the reverse one, I always just add the next character to the left. So I have something and I build it kind of backwards. Just a different way of calling merge. You could also just iterate through this array backwards. That would work too. Okay, so then we go through each query. There are a bunch of different things. If this first query is, I guess it looks range delete. So this is a pretty easy thing to do. We just have to consider what is the range if we go forward and what is the range if we go backwards. So yeah, the range changes obviously. What used to be the left endpoint becomes the right endpoint if we mirror things, and vice versa. And then also we have to do n minus that, minus 1, I guess, is the coordinate that we're looking for. Okay, so what does this range delete look like? Well, it's very simple. We split on the left endpoint, split on the right endpoint, and then merge the two outsides back together. So we've got parts 1, parts 2. We merge the left half of parts 1, right half of parts 2. Insert is just as easy. We split it at the position we want to insert it in, and then we merge the three pieces together. This new thing that we're about to insert, and then also the two other pieces that we just split apart. And then the final part is this range hash. So range hash is, I guess, pretty easy from this perspective. We split the two pieces apart, look at the hash of the middle part. We'll call this twice. So we'll call it once on the treap that we're interested in going forward and once in the reversed one. And that's how we handle those queries. And yeah, all of this main method is we just call those three methods accordingly on both treaps. So both the forward treap and the reversed treap. I guess you want to be careful with your indices. Don't do n minus position minus 1 here. You just got to be careful. And here, finally, we just check if the two hashes are the same. If they are, we print yes, otherwise we print no. Okay, so that's that explanation. I'll kind of scroll through this slowly. If you want to pause the video to see how different things are done here, you can do that. But if you're not into hashing, it's probably fine. Like, this isn't super important. It's kind of like a very specific skill that you need in order to be able to solve this problem. So yeah, I expected this one to be harder than it ended up being. I'm kind of surprised it was the second most solved problem. I thought trick or treat would be much more solved, but it wasn't. That's fine. Let's talk about trick or treat next then. So for trick or treat, it's actually, this is the closest thing that there was to just a copy and paste treat problem. You had to maintain the parent pointers, which was a bit more tricky. But other than that, it was pretty much just do the things that a treat requires. So again, we just have a bunch of different queries. We have to do all of them. The first query is make a new treat node. That's pretty easy. In this case, you just assign it a new number with a new value. So it has some index and some value. You just assign both. The next query is if you have two different treaps. If they're in different groups at the moment, you want to merge the two groups with the left group on the left side, the right group on the right side. If they're in the same group, then you can just ignore it, basically. So in order to do that, you have to be able to see what is the parent of some treap, right? So if you've got like the array you're representing probably looks something like this maybe. So So you've got one group here, one group here, and one group here. And you want to, maybe you want to merge this group here with this group here. So you want this to come here and this to be here. Then you'll have a group of 5. Now, in order for us to handle this, what we need to do is, we've got some Treap represented here. The Treap might look like this. So in this case, we would have, this would be 1, this would be the second element, 2 here, this would be the third element. So that's some possible way the Treap might represent it. And the left to right order here is the same as the left to right order in this Treap. Now, that's fine and all, but if we say, let's say we're given this 2 here, we need to find the root of the Treap because we do all of our operations with the root. So we need to be able to walk up this Treap to find whatever the root is. In this case, it's a 3, or it's this node in particular. To do that, we can store the path parent of, we can store the parent, I guess, of every node in the Treap, and we can just walk up that when we're looking for it. The Treap won't be very tall, which means it'll take most log n steps to find the parent. So we can do that like this. I'll actually look at the Treap code here because here it's very new. We also store this parent, and every time that we change some kid value, in this case we change this kid value here, the first thing we do is we say if the parent of that kid, or if that kid isn't null, then we're changing which parent points to that kid. So that kid used to be our child, and now he no longer is, which means we have to set his parent to null. Then after we set our right kid to be, or I guess this is our left kid, after we set our left kid to be this new element, whatever it is, then we have to remember to update that new element's parent. So we can do that here. This not equals null check is just like to avoid null pointer exceptions because we might not have a left kid. So this might be a non-issue. So basically, yeah, every time you do any assignment for the kid, you have to remember to include these lines. And we do an assignment here, so we have to remember to include these 2 lines here. And then we do another assignment here, so you have to remember to do these 2 lines. Again, all we're doing is we're clearing the parent of the thing that used to be our kid and assigning the parent of the thing that now is our kid. Which means anytime we look down these arrays, because everything happens, like every time we modify the kid array, we'll also modify the parent array. So anytime we look down these arrays, we could just as easily look up the parent array. And that just points us back up the tree. So we have that. That lets us do this thing here, this go up method that I made, which is just keep going up until you don't have a parent. Very easy. Cool. So now when we do all of these operations, type 1 is just make a new Treap, and I just store my Treaps in some array by their index. Very easy to do. Type 2, we merge. So what I do here is I've got 2 Treaps, and these are the 2 Treaps that they tell me to look at. I find both of their parents using this go up method, and if it's the same Treap, I just ignore it. Otherwise, I merge them together like they told me to. And the last type is to do a split. So I have this first Treap. This was a bug for a while. I was forgetting to go up in it. But yeah, so then I find the parent of this node. I find the amount that I'm supposed to split, and then I call split. This will split it into 2 different Treaps. And then finally, this is the query that's like, I guess, the one we have to actually print for, and that's just what's the sum of the group that this thing is in. So I find whatever Treap is of interest, I walk up to its parent, and then I print its sum. And that's the idea. All right, awesome. That is trick or treat. So now we have 2 more problems. This is where things start to get very difficult. In the Speeches and Sneatches, this was a very common segment tree problem. So I'm not going to discuss the idea behind the solution to this problem here. And the reason for that is I already talked about this exact problem, or I guess an easier version of this exact problem. The Speeches and Sneatches 1 I talked about in my segment tree video. So if you haven't seen the algorithm thread on segment trees, it's pretty good, I'd say. And I'd recommend watching it. And at the end, I talk about how to solve this problem if you don't have the queries 2 or 3. Now, if you do have queries 2 or 3, that solution doesn't work. And in order to handle these, you need to have some sort of segment tree that can be modified. Its structure needs to change. The order of some ranges of nodes might need to flip. You might need to transpose them, stuff like that. If you want to do all of that stuff, you want to use probably a Treap or maybe some other type of balanced binary search tree if you prefer those. So what exactly do we need to handle here? Well, first thing is range reverse. Now I talked about this, how to do this in the Treap video. We need some lazy propagation value we should flip the left and right kids of everything in some subtree. We'll first do 2 cuts, then we'll set that lazy propagation value, then we'll do the merges, and the lazy propagation will take care of the operations for us. So we don't need to worry about any of that. We also need this range sort. Now that's a bit tricky because you can't do that. Range sort is not a segment tree operation that I know how to handle, at least. And if this is something that you could do in general, that would be very surprising. It sounds like a really hard operation to handle. However, in this case, all of the numbers are either 0 or 1. So if we want to handle a range sort, all we're doing is setting some range to 0 and setting some range to 1. We also need to know in this range how many zeros and how many ones are there. So I guess that's an important thing as well, because we need to know how many things should be set to 0, how many should be set to 1. But after we sort some range, the prefix will be 0 and suffix will be 1. And then of course we have this usual operation, which is range XOR with 1. Okay, very good. Finally, after this operation, you need to print the same thing, but this is easy enough. We don't need to worry about that. So what do we do? Well, we know how to handle all of these operations separately on Treaps. We just have to be very, very, very careful with calculating the aggregate value for the Treap. So that's where almost all of the code to this problem is and why it's so challenging. Like understanding that it's a Treap problem shouldn't be that difficult, but actually handling all of the different cases is something you have to be very careful with because it's easy to get wrong. So the Treap itself is basically the same as the Treap that you've seen before. Maybe the only difference is that we store a bunch of new things in this data object that I made, which is in the Treap. So what this does is every Treap node that represents some position in the array will have some data object. This represents like whether it's a 1 or a 0, basically. Then in addition, we'll have this subtree aggregate value. Now the subtree aggregate will be for this node and also all of its children. Like how many 1s are there? Does this need to be reversed? Does this need to be set to 0? Does it need to be set to 1? All of that information we'll store in this subtree data object. The reason I keep these separate is because for me it was easier to think about it as I have 2 data objects and I need to merge them into 1. How do I do that in a good way? So in this case, what I'm going to do is you've got this node here. It might have some left child, might have some right child. It also has its own like a data object. So we've got the data object for the left kid subtree and the data object for the right kid subtree. If we want the data object for our subtree, what we need to do is merge these like this, and then we need to merge these. That's the idea. After we do that, those 2 merges, we can get this data object. Now, all of that actually just takes order 1. We can recalculate something in order 1 still. Although it's order 1, it's a ton of code and it's pretty slow, but it's not too bad. So yeah, what does this look like? Like, ooh, man, lots of very scary code. Okay, so much stuff going on. Here's what the data stores. We talked about all of these things in the segment tree video. You need to store, I guess for this problem, you also need the number of zeros and the number of ones, and I stored the width as well because that was like implicitly stored in the segment tree. But you also need, what is the prefix of zeros in this node? What is the suffix of zeros? What is the prefix of ones? What is the suffix of ones? And finally, what's the biggest range of ones within, or biggest range of the same value within this node? So yeah, we need all of these things, which is a lot of stuff we need to store. We also have 4 different ways we might need to propagate. So we might need to set the entire range to 0 or to 1. We also might need to set every 0 to a 1 and every 1 to a 0. we can't do that just naively because we might need to operate on an entire subtree all at once. We want to do that fast. So this has got to be lazy propagation material. Same thing with this mirror. We might need to range mirror some subtree, which means flip the left and right child. So lots of stuff. Okay, I've got these helper methods, so I don't have to worry about these things intersecting with each other. I can keep that all inside this class, make it easier to understand for me. And mirror, I guess, takes the top priority. So if it's mirrored, then it's mirrored. That's easy. If it's not, it's not. Because mirror doesn't really intersect with the rest of the operations. But for these operations, it's a bit tricky. So if we're going to range set something to 0, and we're also going to invert it, the order of those two things matters. If we invert first and then set to everything to 0, we have an array of all zeros. But if we set to all zeros first and then we invert after, then we have an array of all ones. So we have to be careful with these two things, because if they're both true, it might be kind of confusing for us. So yeah, that's why I handle this. If we're all set to one number, then I don't set invert to be true, which means only one of these three values will ever be true at a given time. I guess that means you could use less data. You can represent this in fewer than 3 booleans if you'd like, but I wasn't too worried about that. It's just easier to understand this way for me. Okay, so yeah, either the whole thing is inverted, or the whole thing is all zeros, or the whole thing is all ones. No two combinations of this are possible, and they never need to be either. So this is what the inversion logic looks like. If it's not all zeros or all ones, then we can just flip whether we should invert the whole thing. If it was inverted, uninvert it. If it was uninverted, invert it. Otherwise, what we need to do is, whether it was set to all zeros or all ones, we want to do the opposite. So that's just what this does here. Oops. Finally, we need to be able to set some range to all zeros or all ones. So in that case, we say if it's going to be all zeros, then it's not inverted, it's not mirrored, and it's not all ones, but it is set to 0. So that's the idea. All ones is the same thing, except it's set to 1. Okay, so then we have all of these methods, and there are quite a few of them. They're all very similar in nature, where we want to query something about this aggregate data. Now, this might be tricky, because if we want to say how many ones are there in this group, we might need to look at some of these propagation values. Because for me, what these propagation values represent is things that need to be applied to these values as well. So if it needs to be inverted still, and we have 5 zeros and 10 ones, and we want to know how many zeros there are, well, if this needs to be inverted, we shouldn't actually look at how many zeros there are, we should look at how many ones there are. Which is like why I have all of these methods, basically. So that's the important part. So how do each of these things look? Let's just look at one of them. The rest of them are pretty much the same. We want to see how big is the prefix of ones. How many ones do we start with? Well, if it's all zeros, we don't have any ones, so it starts with 0 ones. If it's all ones, the whole thing is ones, and whatever our width is, that's how many ones we have. If we need to mirror it, then we want to look at the other side. So if this thing is actually mirrored, we want to look at the suffix rather than the prefix. And depending on whether we want the prefix or suffix, we also need to look at whether it's inverted. So if it's inverted, then we're looking for zeros, not ones. And if it's not inverted, we're looking for ones. So there are a lot of just different cases. You have to handle all of them, but they wind up not being too bad. You just go through each of these one by one. There aren't that many different. There's a finite number of them, right? So it's not too bad. Okay, so on top of that, we also need to be able to merge two different data objects. And that's this logic here. This looks like a lot. It's not that bad once you stop to think about it for a bit. But basically what we need to do is say, okay, if we have our left child and our right child, we want to merge them together and say, what is the returned data value? We look at the number of zeros in each, we look at the number of ones in each, we look at the width of each. All of those are very easy. It's just the sum of the two values. The prefixes and suffixes are a bit tricky because the prefix might overflow from the left kid to the right kid. And also, when you're doing this, you want to make sure that the left kid and right kid are actually your left kid and your right kid. So you always want to make sure you propagate before this, so you don't actually pass these in the wrong order and then need to flip them, because that'll mess up your prefix and suffixes if you do it incorrectly. So yeah, so you want to assume there's nothing more to propagate, and that lets you handle these. These are just the same as they would be in a segment tree, so it's not really that special. Finally, you want to calculate the biggest range of continuous values within the segment tree. And you can do this by looking at the 3 different cases. Either it's in your left kid, or it's in your right kid, or it's a 0 that crosses the 2. I guess there are 4 cases. It's a 0 that crosses the middle, or it's a 1 that crosses the middle. So that's what I check here. The biggest range of the same value will be whichever one of these 4 things is biggest. Awesome. Okay. Yeah, so finally, I guess the actual problem is just a matter of calling these values. Do I need to talk about recalculating stuff? I guess maybe. Yeah, maybe this is important. So to talk about, or like to recalculate the aggregates, I just calculate all of the values for my particular node that I represent, and I merge it with the left kid and the right kid if they're not null. That's how you recalculate. Everything else is pretty much the same, I think. So I have these throw nulls just to sanity check myself, because if I'm ever recalculating when I still need to propagate, then something's a problem. Okay, yeah. So that's it. The treep is pretty much the same. It's just all of those extra methods dealing with the data values that's tricky. And what does this actually look like? Well, it's just a matter of calling these methods. So it's pretty simple. If it's a 0, we set these 3 values all to be 1. If it's a 1, we set these 3 values all to be 1. And the width is always 1. The biggest range of continuous values in some element that's all alone is also just a 1. Now we have a bunch of these queries. We either want to invert this middle part, mirror this middle part, or sort this middle part. The sort is just a range set to 0, range set to 1. So not too bad. Okay, awesome. So there you go. Those are all but the hardest problem. And that'll get you 2 different problems, actually, if you're able to implement that, because this Speeches and Sneatches 1 doesn't require treeps. You can only, or you can do it with just segment trees if you're trying to. Finally, the hardest problem is the Grim Treaper. So this was my favorite problem of the set. I thought it was pretty creative because it uses a brand new technique. I guess brand new in the long scheme of things. It's a couple years old now, but it's still pretty fresh. And that is segment tree beats. But it's not just segment tree beats. So even if you have segment tree beats code, you're going to have to model or modify it somewhat in order to get it to work for this problem as well. So what is the problem asking? Well, okay, again, we have some array. We want to do some operations on the array. And what are they? The first thing is we do a slice. We slice our scythe from position L to R. So let's draw a picture to visualize that. We might have some blades of grass that look like this. Okay. Now we do a slice, maybe on these elements here. So now, after we do that slice, this will be this height, and this one will be this height. But these two won't be affected because they were below the scythe when we sliced it. So then afterwards, we'll have an array that looks like this. Yes, this would be a little taller. There we go. So that's the first operation. This is the tricky operation. A lot of people think the tricky operation is this printing the sum, but really everything gets really hard because we're doing the slice. That's what kind of throws a wrench in things, and that's the same reason that segment tree beats are so helpful. Because if you are able to handle this operation the right way, then it makes your life easier later on. Okay, the second part is this range transplant. So basically all of this was some way for me to force you to use a treep. You've got some continuous LR range of interest. Maybe it's this range here. You're going to take this range and move it to the end. So or was it one particular item? No, yeah, it's some range. So you take this here. You move it over to the end, and then afterwards you move everything back so that it looks like this. As an example here, we could take these three, we could take these three elements right here, move them to the end, and then we can move these all back in a row so they look like this. So that's kind of tricky, but that should be pretty easy to handle. If we know we're using a treat for this, which we do because it's a treat practice set, we're gonna cut here, and then we're gonna merge this, but we'll merge this over on this end, and we'll merge these two ends together. So that'll be exactly what we want. Pretty easy there. Finally, we want range add. Range add is easy enough. But range add combined with this first operation is pretty tricky when we also want to know the sum. So, okay, yeah, a prerequisite for solving this problem is knowing segment tree beats. You should know how those work. I have a video on them on my channel, another algorithms thread video, and that explains how they work and when you can use them, some like interesting use cases for them, as well as an analysis of the runtime. So because segment tree beats with range add are n log squared, then this is basically the same thing as the segment tree, except with the treat. Now, the really interesting thing here is that anything you can do with a segment tree, you can also do with a treat. That includes persistent segment trees. You can do persistent treeps. If you want to do segment tree beats, you can do treap beats, I guess. And any other tricks that you have with the segment tree that I know of, you can do the same things with a treat, or with basically almost any other balanced binary search tree. So this just uses one trick in particular that's super helpful, but there are other options as well. You could have a forced persistent segment tree problem, and then you could do that with the treat as well, if you wanted to. It's a bit more tricky though. With the segment tree, you have just two ranges. With the treat, you have two ranges, and then also your middle thing. So usually you have to do two merges to do one recalculation for some subtree with the treat, and with the segment tree, maybe it's a bit easier, but still not the end of the world. Yeah, okay, so how do we actually do this? Well, we store, this is the wrong one. Grim Treaper is what I'm looking for. We store inside this treat, I have a new data object here. This one's a little bit different, but this stores the things that are required in order to do segment tree beats, as well as all the stuff that's required to solve this problem. That is, you need the max, you need the second max, and then to do range sum, you need how many of the max there are, and also how many of the second max there are. We also need the range sum. We also need a lazy propagation value for how much we're about to add. And since we don't have a segment tree, it's helpful for us to store how many things are there in this range. It was easier for me. Because you need this in order to say, if you add 1 to everything, how much did you add? That's like why it's necessary. So constructor is boring, just sets all of those. I also have these methods here because the amount that you're going to add might need to be propagated to this as well, just like we talked about earlier. And if we want to read the second max, it's really the second max plus how much you have to add, which it's easier for me to just call this method than it is to look at this value, also look at some other value. It just saves time when you're coding. Okay, how do you merge them? Well, it's really basically the same thing as how you do segment tree beats. So if you're familiar with segment tree beats code, this is basically the same. You want to maintain the max and also the second max, and that's the idea. I also have these different methods that do the actual queries. So my main method just calls each of these, and this is what I'm looking for. So we'll talk about these first. Range add is the easiest one. If we have some object that we're trying to add to, we just add to that data. This min width and min width safe is, I guess, well, it's a bit messy. So min width safe means I know I'm not going to affect the, I know I'm not going to affect the second max of any of my kids, which means I can just do all of my operations in order 1 right now. I can set some propagation values. I can decrease the max if I need to. If it's bigger than if what I'm minning it with is bigger than the maximum height anyway, I can just return. So this is just easily handleable in order 1. Min width for me, says, okay, you might need to affect second maxes and go down the tree. But this is like not a terrible thing to do because we know whenever we call this method, the array gets simpler. We make the structure of the segment tree beats, I guess, a lot simpler, and we can only do that so many times because for just one range add query, we can't increase the complexity that much. So this is fine for the same reason we talked about one time there. What's interesting here? I mean, not really anything. It's basically the same as how you would do segment tree beat stuff, but namely this if statement, I guess, is kind of helpful, which is if we're going to be less than the second max or equal to the second max, we want to push this down to our kids because the way this will affect what how the sum changes is unpredictable at this point. We're not just setting a bunch of the max values. We're not decreasing a bunch of max values by some amount. We're decreasing max values and also some other values, and maybe some third type of values and some fourth type of values. The way our sum changes is difficult to predict now. So we need to handle this recursively. And then the other case is we can handle it immediately because that doesn't happen. In that case, we just need to know how many of the max thing are there and how much do we decrease it by. Awesome. So then propagation is just, this is the same thing that happens in segment tree propagation. So when we need to propagate something down, we first worry about adding, then I worry about minning width. In other words, some data, the to add needs to be like that happens first to everything in the subtree, then after that the min width happens. But the min width is hasn't been modified by the to add, I guess. So maybe an easier way of thinking about that would be the min happens first, actually. So you min first and then you add. So sure. Yeah. Okay. Awesome. The split, no comments there. Same as before. Same thing with the merge. It's just the recalculate and the propagation. It's very, very tricky. All right. Yeah, it's not actually that challenging then. The rest of the problem is just call the methods that I made earlier, but making those methods and making the recalculation and getting that all right is something that takes a bit of practice, I'd say. So it's a good thing to have done once or twice before in case something like this shows up as a subproblem in a hard problem and Code Forces Around or ICPC kind of has something like that. Awesome. Okay, so yeah, those are the 5 problems. Congrats to a lot of people for solving all of them. We had 15 people, including thallium is vegetable, solve all of the 6 problems. There were also some people who solved it in upsolving mode. So I don't know if I can see them right now, but they solved it as just for fun. And I'm not logged in for whatever reason. Yeah, so nice job. I also saw Ben Q solved the hard problem, so that was fun. It's always fun to see someone who's wicked good, still getting some value out of your problems. Okay, that's everything from me. You can check the links in the description if you want to see some of this code or the generators that I used for them. I'll post those as well. Thank you for watching, and have a great day. Goodbye.